Okay, so last lecture, we have seen an interesting property known as Bolzano's property, and which you can refer in your whenever you are dealing with the problem as well. Referring Bolzano's property, the result is follows. Okay, so which was such that let I is an interval and f be a continuous function on the interval I. So if either of these two satisfied, or in other words, if you are able to locate that the values a and b such that f of a into f of b is less than 0, product is less than 0, then you will be always able to find a point c inside the open interval ab, so that f of c is equals to 0. Okay, right. So this Bolzano's property gives the guarantee that there is at least one real root for a continuous function which satisfies the following property. Means if you are able to locate that two points A and B such that the images, corresponding images are of opposite sign, then you will always be able to identify a root of f on the C inside the interval AB. Okay, so then we had a discussion about that there is this gives you guarantee that there is at least one real root. Then we had a discussion regarding whether it will be odd number or even number. So I have an example here which is as follows. So I have defined the function f of x equals to x for x belongs to -1 to 1, and for x belongs to 1 to 2, it's the line again minus x plus 2, and for x belongs to 2 to 3, we have this following function is defined on the interval -1 to 3. Okay, and you can see that f of -1 into f of 3, then you can say this is going to be negative. So f of -1 is -1 and f of 3 is 1. So both are of opposite sign. Okay, and over you can check the continuity of the function at the end point of the interval. So you can only worry about the edges x equals to 1, at x equals to 2, and at x equals to 2. Okay, so if you are able to identify that function is continuous over the interval -1 to 3, then Bolzano's property gives you guarantee that there is at least one root on the interval -1 to 3. But if you look at the graph, there are exactly two roots. Okay, so we can't say here there is at least one at least odd number of roots. If the root are there, there will be an odd number or even number. Okay, what we require is here is smoothness of the curve is required. Okay, so then it may if the curve is smooth, means if you have include the differentiability, then the situation may change. So then in the case, then you may have the kind of parabola, and that will have the double root on the x-axis. So then you will be able to justify that there will be odd number of roots if there is at least one root. Okay, so that we will look after maybe later on stage. Okay, now this property is useful for identifying the root of the equation f of x equals to 0. So this f function, if you have been given with a polynomial of degree 2 or degree 3, or at most degree 4, so it is you know how to handle them. Okay, so for biquadratic equation, you know Ferrari method is there. You know for quadratic equation you have the direct formula is there. For cubic equation, you know that at least one real root is there. Okay, but what about the equations which not only involve the function of the power of x, they also involve the transcendental functions. So transcendental functions are exponential function, logarithmic function, and trigonometric functions are known as transcendental function. So if you have the equation like cos x into cos x plus x equals to 0. Okay, so such equations can be solved by using this method. So how we can use this Bolzano's property to locate the root of such type of equations, that is we are going to now explain. Okay, so here is our which is known as bisection method, which is also known as interval halving method. So by the name, it is clear that interval halving method means it is at each step, it is going to consider the half of the interval. Okay, that will be clear soon. So it is used for locating root of the equation f of x 0 and locating approximately, you can say. Okay, it may not locate the exact root, but it may locate the approximate root. Okay, so for this, applying this method, f must satisfy Bolzano's property. Okay, which is you are supposed to identify 2 points A and B in R such that f of A into f of B is less than 0. That's the first thing. And the second thing is f must be continuous. These two conditions need to be satisfied. Then the Bolzano's property guarantees that you will always able to find that C in A B such that f of C is 0. Now, how this method will work? So once you identify the interval, A to B, then how will you proceed? So what you will do is first, so here are the steps now. Locate A and B in R such that f of A into f of B is less than 0 and f is continuous on the interval A to B. So these two things are necessary. You can't avoid any one. Okay, right. And then we just because it's a process, it may be non-terminating process or it may be terminating process. Okay, so what you will do is I will for starting stage or first step, I will identify this A, the left hand point as by A1 and the right hand point by B1, and then I will call this interval I1 as A1 comma B1, this closed interval. And what I will do is geometrically it is I have defined this x1, the point is the midpoint of the interval. Okay, so if I so you have the point, this is here, so the point A, the point B, then x1 is the midpoint of the interval. Then what you will do? You will check the sign of function f at this value x1. Okay, so what happen is either f of x1 is, so the only three cases possible. Either f of x1 is negative, or f of x1 is 0, or f of x1 is greater than 0. There are only three cases. Okay, so for simplicity, since we have not assumed anything that f of A is negative or f of B is positive or f of A positive or f of B negative, so for simplicity, we assume that f of A is negative and f of B is positive. Similarly, you can discuss the case when f of A is greater than 0 and f of less than 0. So for starting point of view, so we have assumed that f of A is less than 0 and f of B is greater than 0. Now you can discuss the case now, f of x1 is less than 0. Suppose f of x1 is less than 0. Then, since function is continuous on the closed interval A to B, okay, so it will continuous on this interval A to x1 and also it is continuous on x1 to B. Okay, so that we are not worried about the continuity. Okay, now the next thing is function of x1. Suppose function value at x1 is negative. Okay, so then you can see that f is continuous over the interval A to x1 and also f is continuous over the interval x1 to b. So then Bolzano's property guarantees that the root must lies between the interval x1 to b. Okay, because f of x1 is less than 0 and f of b is greater than 0. Okay, there may be a chance that it is coming down from the A point, it is coming down and then it is going up. Okay, that is also possible. Okay, but what because we can't say here surely that what is happening between A and x1, whether there is any root between them or not, we don't know. But we surely know that if f of x1 is less than 0 and b is greater than 0, then Bolzano's property guarantees that there is at least one root. So for the next step, interval is x1 to b1, x1 to b. Okay, so that we will call the interval then. Okay, so we are going to now consider geometrically the next interval is x1 to b, and then we will call this as this b is b2 and x1 is a2, and we will repeat the above process, okay, for the next step. Then again you will go for the midpoint of the interval, and then you will again check the sign. Okay, now if the case f of x1 is 0, process ends here because we have found the exact root. So they say this will end the process. Now if in the case of f of x1 is greater than 0, what will happen? So f of x1 is greater than 0, so f of b is greater than 0. So we don't know, because Bolzano's property will not guarantee that this root lies between x1 to b. But f of a is negative and f of x1 is positive. Means Bolzano property guarantees that the root lies between in the interval a to x1 for this case. Okay, so then we will identify the next interval by a is equals to a2 and x1 equals to b2. Okay, and then we will repeat the process again for this case. Okay, so these are the three cases. Okay, let's here. So f of x1 is less than 0, then root lies in the interval x1 to b1. So that's just now we have seen. Okay, so we will call that a2 is x1 and b2 is b1. Okay, means left hand point is a2 and right hand point becomes whatever it is become. Okay, that is going to be b2. Now in the case of f of x1 equals to 0, then x1 is the root. Method stops here. Now if f of x1 is greater than 0, then root lies in this interval a1 to x1. Then means we will call this a2 as a1 and x1 as b2 as x1. Okay, so in any of the case you are obtaining a new interval a2 to b2, which will be the half of the previous one. Okay, means what is the, if I want to say here, let me, so what is the relation between this new interval? So I have this I2 is equals to A2 comma B2. So which is going to be subset of A1 comma B1, because you are subdividing the interval and you are considering the half part of the interval. Over B2 minus A2, the length of the interval is nothing, a half of the length of the interval A1 to B1. Now the next interval which you are going to generate, that is you are going to call I3. Okay, so the above process. So in this you are going to new interval will come as I3. That is going to be A3 comma B3. How would you obtain is, you have this is A2 comma A2 B2 interval, and you are going to call this is the midpoint of the interval. Then you will check the sign of f of x2 is so here what is other is f of a2 is negative and f of b2 is positive. Okay, f of a1 was less than 0 and f of b1 was greater than 0. Okay, what we have obtained, f of a1 was less than 0, we have started with f of b1 was greater than 0. Okay, so now you will check the case now f of x2. So f of x2 is greater than 0, then a3 comma b3. So a3 is equals to a3 equals to, so f of x, so a2 is less than 0, f of a2 value is less than 0 and f of x2 is greater than 0. So a3 is a2 and b3 is x2. So in the case this, so in the case of f of x2 equals to 0, method stops here. Okay, this will be the root. Okay, we will not proceed further. So f of x2 is less than 0 in this case, you have this a3 is equals to, so f of x2 is less than 0. I don't know about a2 to x2. I know about x2 to b2 because f of x2 is less than 0 and f of b2 is greater than 0. So a3 is x2 and b3 is b2. So your new interval I3. So again, you are subdividing the interval now. So I3, so what you are getting is, so you are getting the following things now. Okay? That I3 is contained in I2, is contained in I1. And what is B3 minus A3? Is nothing but the B2 minus A2 by 2. This interval half length. Okay? And B2 minus A2, what was that? Is B1 minus A1 by 2. So that is going to be 2 square. And so on. So what you are going to say, if the process will not end, you are going to find a sequence of intervals in, an comma bn, and this is a decreasing sequence. Okay, so in is a subset of in minus 1, subset of in minus 2, subset of, and so on, the subset of I1. And what is there is bn minus an is equals to, you can show that by following the process, that you can show that that is going to be 1 minus a1 divided by 2 to the power n minus 1. If you look at n equals to 3, 2 square, n equals to 2, you have 2. Okay, so right now, so in the limiting case, so what is the limit? So before talking about the limit, first we have to talk about whether, so this, the limit of this is limit of bn minus an is equals to the limit of this b1 minus a1 by 2 to the power n minus 1, and that is going to be 0. Right? That we have notion, because b minus a, this is a fixed number, and you have this 1 by 2 to the power n minus 1. And so limit of this as n goes to infinity, this goes to 0. Okay, what more you observe is, f of, so if you look at any interval ik, so you have this ik interval, ak comma bk, then if you look at the properties, f of ak is less than 0 and f of bk is greater than 0. That's the first thing. Okay, that's the first thing. Second thing is, you also note that the relation here. So A1 is less than equals to A2, less than equals to A3, less than equals to, and so on, less than equals to AN. Means you are increasing, right? This A1 is a increasing sequence. Okay, A1 is a monotonically increasing sequence, and so on. That certainly less than equals to here Bn. Less than equals to bn minus 1, less than equals to, and so on, less than equals to b1. So what you can observe is the sequence an is monotonically increasing and bounded. Moreover, the sequence bn is monotonically decreasing and also bounded. So monotonic convergence theorem tells you that both will converge. Okay, so monotone convergence theorem. So what we have understood from the previous lectures, a monotone convergence theorem implies this an and bn converges. But where do they converge? They will converge to the same limit. Okay, why? Because if you look at back here, so limit of bn minus an is 0 and both are convergent. So limit of bn minus limit of an, that is equals to limit of bn minus limit of an is equals to 0. And that will give you limit of bn equals to limit of an, and that is equals to some number that is called c. So and limit of an is equals to limit of Bn, and that is equals to C. Okay. Now we are going to use the fact that function is continuous. Okay, so function is continuous and you have the sequence an, okay, which is converging to C. Okay, so then function f of an will converge to f of C, the continuity sequential criteria. Okay, similarly bn sequence converges to C, and then continuous function, because function is continuous, f of bn will converge to f of C. Then we will discuss about the what is f of C value. So C must be lies inside the interval AB. C must be inside the interval A to B. Okay, that is a part of every interval IK. Means this intersection of this IK will never non-empty. Okay, that you can show. Okay, so now you will show that we will show that f of C is in fact 0. Okay, by looking at the fact that because f of AK is less than 0, and you know that limit of f of AK will be less than equals to 0, because we know that limit of sequence of positive real numbers will be positive. So limit of sequence of negative real numbers will be negative. So we are going to use those facts here. So then you will obtain the result. Okay, right. So I have already explained this. In any of the above case, root will lie in this. Okay, I have already explained this. So we will obtain the following. Okay, so we will obtain this following decreasing sequence of intervals in this non-terminating process. If the process will not terminate anywhere, where f of ak is less than 0 and f of bk is greater than 0 for every k equals to 3 and so on. Okay, and we have also shown that an is monotonically increasing, bounded. Bn is also monotonically decreasing, they are also bounded. So that will imply the both are convergent because of monotone convergence theorem. And we have also shown that limit of an is equals to limit of bn, if that is equals to C. Okay. Now, f is continuous. F of an will converge to f of C because an is converging to C. Okay. Similarly, f of bn is also converged to f of C. Now, since f of an is less than 0, so its limit will be less than equal to 0. So, what is the limit value is f of C. So, f of C must be less than equals to 0. Now, the next case, f of bn, limit is f of C, but f of bn all are positive, strictly greater than 0. So, limit will be greater than equals to 0. So, f of C is less than equal to 0, f of C is greater than equals to 0. Only possibility f of C is 0. So, in the limiting case, that's going to be the converge to the root of the. Okay, so the bisection method will give you the root of the equation f of x equals to 0, and I will explain you the how will you apply the bisection method. Okay, right. So let's take one example that's straightforward from your book. Okay, find an approximate root of the following equation x into e to the power x minus 2, that you cannot solve, right, simply analytically. Okay, it's not easy to solve this equation. Okay, right. So you want to locate the root of this equation. Okay, right. So you can you have to locate function. So this function you can identify this function. This product of two continuous function is continuous. Sum of two continuous function is continuous. The function is continuous. Okay, and then you take the insight of the graph as well. Okay, you know that e to the power 1 is 2.7, e power e minus 2. So if you take x equals to 1, if you take x equals to 1, so you will have f of 1 is equals to, it is something 2.7 minus 2, so that's certainly greater than 0. And f of minus 1 is less than 0 because f of minus, because e to the power minus 1 anyway positive, 1 by e. So minus time something positive is negative, negative, and some two negative number is again negative. So that's certainly less than 0. So you can start with this interval and you can locate the root. Apply the bisection method. Yeah.
We can start with 0 only now, sir.
Yes, you can start with 0 as well. Yes. Yeah. Yes. F of 0 is, yeah, -2. Yes. You can start with this also. 0, 1. 0, 1 interval also you can start. Okay. And they see it will use only one step. When? Because, why? Because 1 to you have the interval -1 to 1. So what is the midpoint of the interval is 0. Okay. So you will increase one more step here. You will increase one more step here. So yes. So you have to identify the two points where the function becomes, one of the value is negative, one of the function value at point is positive, and then you can apply the bisection. Okay, so here you can start with the interval 0 to 1. Okay, so here is this for n equals to 1, 0 to 1. Then this Pn, this is Pn is nothing but this your midpoint of the interval xn, and these are the values f of xn, and these are the so at every step the length of the interval is decreasing by 2. Okay, so here 0, 1, so midpoint is 0.5, and if you find out the value f at p1 or x1, okay, that is going to be negative. Okay, and you have seen that f of 0 is also negative. Okay, and f of 1 is positive. So the next, the root will lie, Bolzano property will be applicable in the interval 0.5 to 1. So the next interval is 0.5 to 1. Okay, you take the midpoint, this is x2, 0.75, and then if you see the value is going to be again negative. So f of 0.5 is -1, so negative, this is also negative. So the next root will lies between 0.75 and 1. Okay, so this is the next interval A3, B3. Take the midpoint of the interval. Okay, now you look at the value at 0.875, the midpoint, that's going to be positive. Now f of 0.75 is negative, f of 1 is positive. So the root certainly lies between 0.75 and 0.875. That's going to be the fourth interval, and so on. Okay, so at each step you are supposed to check the sign of the value of the function at the midpoint of the interval, and then you are proceeding. Okay, so this is a non-terminating process at present. Okay, so the question is, where do you stop? Okay, so the stop when you will stop is whenever you are starting getting values, means like desired accuracy, means like previous value xn minus 1 mod is, if you're writing the code, that's going to be less than epsilon. Epsilon is, you can define as in your code is 10 to the power minus 6 or 10 to the power minus 2. So you can stop by using the stopping criteria, or you can fix the number of iterations. It's like you are going to only going for till 8 number of steps or 10 number of steps. You don't care what is the accuracy you are achieving. Okay, so these are the possible stopping criteria at present. And you can see, you can go back and check also, you can see that this method will never fail. Okay, whenever you are, because it's using the Bolzano's property, and Bolzano's property gives you guarantee that there is a root. Okay, so it will never fail. Okay, so but what is the drawback of this is it has a convergence rate of the, means convergence rate towards the root of the equation is slow. Okay, that is one. Okay, we will talk later about this rate of convergence more. Okay, if we get a time, or if we see another method also. Okay, so this method has a very slow convergence rate. Okay, that's equals to 1. Okay, so we are not going to discuss that how this rate of convergence is 1. Okay. Right. So this is one of the method, okay, which you can consider the part of your project later on. Okay. So now the next very immediate result of this Bolzano's property is the intermediate value theorem. Means if you have the function is continuous in a closed interval I. Okay, so if let I be an interval and let continuous on I, then if you take any values in the values f of a and f of b, then you will always able to identify a point C over the interval AB such that f of C is K. Okay, the situation is like you have the here. This is the here, so function is continuous. So here this is, let's say this is your f of A and this is of B. So if you take any value here K, so you will always able to identify, locate the point or this interval in the interval A to B, that point C, such that f of C is that value K. Okay, the provided function is continuous. Okay, so if you here, so only we are going to use the fact that we are going to use the Bolzano's property here. So you are defining a new function g by g of x equals to f of x minus k. Okay, now see, if you take the difference with k in this inequality, f of a minus k is less than 0, less than f of b minus k. Okay, so means it gives you something feeling like Bolzano's property. So this is why here the considered function is g, that is defined by f of x minus k. Now since f is continuous and k function is constant function is also continuous. Okay, the sum of two continuous function is continuous, so g is continuous on I. And also you can verify that g of a is f of a minus k, but that is less than 0. G of b is f of b minus k, that is greater than 0. So product of g of a and g of b is less than 0. So g is continuous and you have on the interval I, and g of a and g of b is less than 0. So this the Bolzano's property implies that it has at least one root in the interval C, such that there will always exist a C in I such that g of C is 0. Then g of C is 0 means f of C is K. That's it. That's it. Intermediate value theorem. Okay, right. Yeah. So this is explained now. Okay. Now the next our is topic is differentiability of functions of single variable. So if you recall your fundamental definition of differentiability, so you have this is if it is exist f dash of c, if you look at, so that's going to be limit x tends to c, f of x minus f of c divided by x minus c, if this exists. So this is going to be the limit value of this function. So f of x minus f of c divided by x minus c. So that you call that L, this L or f dash of c. So that both are the same. If we write f dash of c is L. Okay. So in terms of epsilon delta, you can always, so this is a limit of some function g, you can say g of x. Okay. So limit of g of x equals to L. So then you can write the definition carefully. So let I be an interval, let f from I to R, and let C is in I. Okay, we say that a real number L is the derivative of f at C if given any epsilon bigger than 0, there exists delta which may depend on epsilon greater than 0 such that this happens. So this function will getting closer to L whenever x is getting closer towards C. Okay, so C here it's x is not equals to this, taking the range, you are taking the deleted neighborhood of C here. Okay, because this function is 0 by 0 form whenever x equals to C, that's the indeterminate form. Okay, so you are talking about the limiting value. So if f fails to be differentiable at C, then we say that f is non-differentiable at C. Okay, and you know what is the function if you look at f of x equals to mod x and x belongs to R, then you can show that f is not differentiable at 0. Okay, that limit value Okay, f dash at 0 which does not exist. Okay, means like what is that? Limit of x tends to 0, f of x minus f of 0, that is mod x divided by x. That's going to be 1 if x is greater than 0 and minus 1 if x is less than 0. The limit does exist, but sorry, not this left hand limit and right hand limit does exist, but they are not equal. So the function will not be differentiable at the point C. Okay, I mean, at the point 0 here, x, and so this C is 0 here. Okay, elsewhere it is differentiable as well. Okay, except at 0 it is differentiable. That you can also show that. Okay, right. Whenever x is positive, the derivative is 1. Whenever c is greater than 0, the derivative is 1. Whenever c is less than 0, derivative is then minus. Okay. So this is a fundamental definition of in terms of epsilon delta for differentiability of functions of single variable. Okay. Now that immediate from above, you can verify that if function is a derivative at c, then f is continuous at c. You have to just, you know, that you can write f of x minus f of c. You divide and multiply by x minus c. Okay, and use the fact that f is differentiable at c. Okay, then you can show that f is continuous at c. Okay, so it's very simple. F of x minus mod of f of x minus f of c, you can show that this is out of f of x minus f of c by x minus c times mod x minus c. Now you can use the fact that this minus minus f dash of c plus f dash of c, so that you can add and subtract in this here and use the triangle inequality. So this is going to be less than equals to, I'm going to add and subtract minus f dash of c plus f dash of c here in this magnitude, inside magnitude. Then you will use the fact that this is going to be mod of f of x minus f of c by x minus c minus f dash of c plus mod of f dash of c time mod of x minus c, and you know that that is less than epsilon whenever 0 less than mod x minus c less than delta. Okay, and this is a bounded number, so then you can create an artificial delta for this f of x minus f of c. Okay, so you no need to worry about at x equals to c, because at x equals to c, f of c minus f of c is 0. Okay, so we don't worry about x at x equals to c value. So this mod is always is equals to 0 magnitude value. So we only worry about when x is not equals to c, x is going closer towards c, whether from the left or from the right. So you can create an artificial delta such that this is less than epsilon. Okay, right. So whenever a function has a derivative, then f is continuous at c. Okay, but converse is need not be true. We have already seen the modulus function. Okay, so modulus function is continuous everywhere on R. Okay, if you talk about at 0, it is also continuous, but it is not differentiable at 0. Okay, right. So the continuity of the function becomes the necessary condition for the differentiability. Okay, right. So I have already explained the example for show that continuity may or may not imply the differentiability of functions. So I have already explained that this example, you can take the similar example. F of x equals to mod x whenever x belongs to minus 1 to 1. The function is continuous everywhere except continuous everywhere on the interval minus 1 to 1. So function is continuous at 0, but function is not differentiable at 0. Okay, that just now we have seen. Okay, so this is the algebra of the differentiability here, you can say. The sum of two differentiable function is differentiable, difference of two differentiable function is differentiable, product of two differentiable function is differentiable, and how they have, or you are obtaining chain rule, okay, or product rule here, sorry. Here is product rule, you know how to differentiate, you know that first function as it is, second function derivative plus second function as it is, first function derivative. Okay. Similarly, scalar multiple of a differentiable function is also differentiable at C. So here, sum of two differentiable function, difference of two differentiable function, product of two differentiable function are also differentiable, and you can obtain this result, that the product of how to differentiate the product of two functions. Okay. Similarly, for the quotient rule. Okay. So before the quotient rule, you need to, at first hand, g of c should not be 0. Okay, that should be required, and you know that how to apply the quotient rule. So whenever whenever function is f is differentiable, g is differentiable. This rational function is also differentiable at that point c, provided g of c is non-zero. Okay, so it will give you the, means you can now discuss about the rational functions now. Numerator is polynomial, denominator is polynomial. So you have to work out the zeros of the denominator. That's what this gives you the feeling. Okay, and you can discuss the differentiability of the function by referring this result. Okay, now this is a composition of two functions. So like we have discussed for the continuity case. So let I and j two intervals, and let g is from I to R and f is from I to R. Okay, so f is from j to R. Okay, be functions such that the range of f lies inside I, and let c is in. So you are going to define the g composed f, and you are discussing the differentiability at c. Okay, and if you know that if you open up, that's going to be first you are going to differentiate g, and then you are differentiating the argument f of c. Okay, so g dash f of c and f dash of c. So means what you require, function f must be differentiable at c, and g is differentiable at f of c. Then the composite function is differentiable at c. Okay, so now you can discuss about the functions like mod of sin x. You can discuss about the function mod of sin x. Okay, and other functions is like mod of cos x plus x square, or another function e to the power 1 by x. Okay, and so on. So you can discuss about the differentiability of these functions. Okay, by using this chain rule. Now, what is the application of differentiability? We are going to now look at it. Okay, so first here we are going to define the maxima and minima, okay, of function. So we have already seen one theorem called boundedness theorem, which says that if f is a continuous function on a closed interval I, then that is bounded. F is function is bounded on I. Means f attains its bounded value, like means maximum and minimum values. Okay, right. That's what it. That's what the boundedness theorem implies. Okay, so right. So now certainly we can talk about them. What will be the maximum value of f? What will be the minimum value of f? Means the function f is bounded, means the set f of x such that x belongs to A. Here, suppose I say this set is bounded. Means what? I can talk about its infimum and I can talk about its supremum. And once the function is continuous and the set A is closed interval I, the both infimum and supremum will exist at some point inside A. Okay, so that supremum and infimum becomes the absolute maximum and absolute minimum for the set A. Okay, so here is the definition. So for the general interval A, so let A is a subset of R and let F is from A to R. So we say that f has an absolute maximum on A if we are able to identify a point x star. So we are having the superscript with star here, and here is the subscript of the star. Means that's going to upper and that's going to be lower, means correspondingly absolute maximum and absolute minimum. So if there is a point x star in A such that f of x star lies right of f of x, means for any value of x in A, f of x star is lies on the right of it. But x star is inside A. It is not that. X star must be inside A. We are able to identify a point x star inside A so that this f of x star is greater than equals to f of x for all x in A. Then you will say that x star is a point of absolute maximum. Okay, or in other words, f has an absolute maximum on A. Similarly, for the case f has an absolute minimum on A, if there is a point x star in A such that f of x star is lies left of f of x for any value of x. Okay. And x star, this x subscript star is also the points of A. If you are not able to identify any point inside A which satisfying either one of them or none of them, means the function does not neither have absolute maximum. If you are not able to identify this, if there is not exist any point in A such that this happens, then f does not have any absolute meaning. For example, this is the example here. For a function f of x equals to 1 by x. So if you consider the interval a1 is 0 to infinity, infinite length interval, you know that for x greater than 1, then 1 by x is less than 1. So for the values x on the interval 1 to infinity, okay, for the interval 1 to infinity, you know that 1 by x is less than 1. Okay, and you can see that at x equals to 1, that is 1. But it is not true for every, right? For x less than 1, 1 by x is greater than 1. So I can say here, I will not able to identify any point on the interval this a1 such that f of x is less than equals to that f of x star. So I am not able to identify this. Similarly, I will not be able to identify a point inside A which is such that f of x star is less than equals to f of x for all x in A. So neither is possible for this case, a1 to 0 to infinity, on this interval 0 to infinity. Okay, so what you will have is here is, so that therefore this function does not neither have absolute maximum nor absolute minimum on the set. So we have considered the infinite length interval. So whether it is also, whether it will not be true for finite length interval, you can look at here. For a2 0 to 1, you know that limit x tends to 0 plus is infinity, that you can show. That's a very large value. But 0 is not the part of this interval. Okay. Similarly, 1 is also not the part of this interval. So x is less than 1, so 1 by x is greater than 1. Okay. So 1 by x, right? So this function will also not have neither absolute maximum and nor absolute minimum on this interval. So it is not completely depends on the length of the interval. So it may be possible that you have a finite length of interval, but the function may not attain the absolute maximum or absolute minimum.
Sir,
Okay, yes.
sir,
So
if in
if you
A2,
include the 0 here, if you have the 0 here, yes.
no, sir, if we include 1 inside A2,
Huh.
then will 1 be the x star?
One will be the
minimum.
absolute mix. What can you say? Absolute minimum. It will be.
Yes. Will it be
Yes.
possible?
Yes. Yes. Because in this definition, you are that absolute minimum point must be inside A. If it is not here, it is not inside A. That will not have a maximum or minimum inside on A.
But sir, in A2 also there will be a point that is the lowest value. That is just before a limit uh, x tends to 1 minus.
1 minus what?
The number, let's suppose the number is c. C equals limit x tends to 1 minus.
Ah,
That
that
number
is
will be the absolute minimum of that function and it is inside A2. So why don't
but
we consider that number?
no, that 1 minus is an abstract number. That's a limiting number. It's not means like you can't identify that. What is that 1 minus? That 1 minus is something like 0.99999.
Okay, sir, understood.
Okay. So there are infinitely many number between 1 and 1 minus. Okay, these rational numbers are there, irrational numbers are there, density theorem. Okay. So for having the absolute minimum for this interval A2 on the interval, you must include 1 inside. Okay, absolute minimum. So now if you take the interval like 1 to 2, suppose I take the interval 1 to 2, then you can certainly talk about both. The 1 by x function is you have decreasing function, right? So it will have the maximum at the left hand point and right hand point. At the right hand point, it's the minimum, absolute minimum, if you include this 1 to 2. Okay, right. Now we have the following. So I already this is a corollary, you can say, corollary from the boundedness theorem. Boundedness theorem will imply this, that if function is continuous on a closed and bounded interval, then f is bounded and it has an absolute maximum and absolute minimum on I. So this boundedness theorem will imply the following result, which is known as maximum minimum theorem. Okay, so that we are going to use as it is in our course, that if f is a continuous function on a closed interval and also interval is not closed and also bounded, then it has absolute maximum and absolute minimum on I itself. So we don't know whether it attains a minimum at f of a and x maximum at f of b. Okay, so for example, we have just now we have seen f of x equals to 1 by x is continuous on the closed interval 1 to 2. Okay, then maximum minimum theorem, it tells you that it attains its absolute maximum and absolute minimum on this interval itself. So what will be that point? That is need to be located. Okay, right. Okay, so now since it is not feasible to look at the globally, means like maximum globally and minimum in global sense. Okay, so definitely you are certainly lie down to the local. Okay, so this is here is relative maxima or relative minima. So we say that f has a relative maximum at C. So this is something different from absolute maxima or minima. Means the function is defined on the interval A, and we are trying to find out a point x star A, so that f of x star is greater than equals to f of x for every x in A. Similarly, we were trying to identify the absolute minimum, which is lies completely left on the f, means all the values of f of x. Okay, so here we are only particular about a point inside C, inside I, a C in I, and we are saying that f has relative maximum at C. Okay, means you have a function behavior and you are only considering small part of the interval I. Okay, so if you are able to identify a neighborhood over which this f of c is greater than or equals to f of x for all x in v intersect with I. Function must be defined on this way. Okay, so if you are able to identify a neighborhood of c such that f of c is greater than or equals to f of x for all x in v intersects with I, then we say that f has relative maximum. So if you have the opposite one, f of c is, suppose you are able to identify a neighborhood of c such that f of c is less than or equals to f of x for all x in this, then we say that f has relative minimum at that. So this is a local, means you are able to identify a neighborhood of c where you can see that this f of c lies above the f of x, and with all the values inside that neighborhood, and similarly for relative minimum. Means you are looking at locally, not global, means on the throughout the interval, only local. Okay, so if either one of them is there, we say that's relative extremum. Okay, so relative extremum means at point C is either it is relative maximum or it is relative minimum. Okay, so means like what is here is, if I want to draw the curve, it's like you have this is like this is here like this. So you know that, see, if it suppose this is the function. So if you look at the graph, so this is the absolute maximum at this point, and this is the absolute minimum. But what about this is a relative maximum, and a relative maximum here, and this is a relative minimum at this point. Okay, so it is not always, you are not able to always possible that to discuss about the global minimum or global maximum or absolute maximum or absolute minimum. So we are lying down to do now local case. Okay, right. Okay, so we have some now very important result which is known as interior extremum theorem. Okay, so which is as follows. So interior extremum theorem, what it says, so you need to be careful about the conditions here. So let C be an interior point of the interval. So please note that C is an interior point of the interval. Okay, so it is not the boundary point. Means if you have the I closed interval A to B, so C is not A, neither A nor B. It is a point inside A to B, open interval AB. Okay, we are going to look at the case there. Those also we are looking. Okay, so at which f has a relative extremum. So suppose C is an interior point of the interval I, and f has a relative extremum. If the derivative of f at C exists, then f dash of C is 0. So, for example, let's say, let me give you one example that, let's say, f of x is equals to x over the interval x belongs to 0 to 1. Now, see, if you look at the derivative value f dash at x, that is going to be 1, which is not 0. Function is differentiable and it is non-zero for any value of x belongs to 0 to 1. But it has an absolute maximum at 1 and absolute minimum at 0. It's at a relative at 0 and 1. 0 and 1 are the boundary point of the. Okay, they are not the interior point of the interval. So this theorem still remains true because we are talking about the interior point of the interval at which f is relative. So if the derivative of f at C exists, so there may be a chance that derivative may not exist. Okay, derivative may not exist. So for example, for this case, f of x equals to, you can take mod x for x belongs to -1 to 1. So function, function is minimum at x equals to 0, and 0 is an interior point, right? So 0 is an interior point and f is minimum at, has relative extremum at 0, but function is not differentiable. So that is why still, so if the derivative of f at C exists, then f dash of C is 0. So still this theorem will not help in this example. Okay, so let C be an interior point of the interval I at which f has a relative extremum. So it may be relative minimum or relative maximum. So if the derivative of f at C exists, then f dash of C is 0. So if the derivative exists, then f dash of c is 0. So this is why when you are trying to solve the problem for maxima minima, okay, or in other words, you are trying to identify the relative maximum and relative minimum values. Okay, so once you verify that function is differentiable, then you look at the points, you are going to locate the points f dash c such that f dash of c is 0. Also, you will locate the points where the derivative does not exist. And if you're talking about the absolute maxima and minima, then you are also list the values of boundary point of the interval. Okay. So this is the next case. Those points are known as extremum points. So such points, this C is known as extremum points or critical points in other words. Okay. Right. So let's for the proof is very simple. So let f has a relative maximum at C. So you can the proof will follow for the relative minimum as well. Similar manner. So let f has a relative maximum and suppose that f dash of c exists because this. So either f does not exist, so you are over. And the derivative does not exist, you are over. So there is nothing to prove. So if the derivative exists, means f dash of c exists. Then we are going to show that f dash of c is 0. Now, so we are going to claim is f dash of c is equals to 0. So there are three possibilities. F dash of c is less than 0, equal to 0, or greater than 0. If you strike out f dash of c is greater than 0 and less than 0, those possibilities, then only possibility remain is f dash of c is 0. Now, so let's consider the case f dash of c is greater than 0. And now look at the definition of f dash of c carefully. That is a limit of f of x minus f of c divided by x minus c. Okay, and that is limiting value is greater than 0 means the function will also remain positive in some neighborhood of c. If you recall that result which I have mentioned there, that function is, so I'm going to use this fact now, that so if you have limit x tends to c, f is greater than 0, then f is positive in some neighborhood of c. Okay, there will be a neighborhood where x still remains positive. So we are going to use this result now to establish our claim. So what it will give you is, let f dash of c is greater than 0. Since f dash of c is this and this is greater than 0, will implies you will always able to identify delta such that this happens. F of x, this function will remain positive inside that neighborhood. Okay, and x not equals to c here, surely, because it's indeterminate form for x equals to c. Now, so since x, so you have this is f of x minus f of c divided by x minus c is greater than 0 for all x belongs to v delta of c subset of I. So this will implies that f of x is must be greater than f of c for x belongs to v delta of c, which is contradiction to the fact that f of c is relative maximum, because it's not a relative maximum, because you are able to identify a neighborhood where f of c is less than f of x. So this neighborhood will certainly include some of the points of other neighborhood as well, whatever the neighborhood you take of c. So this neighborhood will certainly be also include the point, okay, which is the part of the all other neighborhoods. So this will contradict to the fact that f of c is a relative extremum. Okay, relative maximum, you can relative maximum. So f of c is lies below f of x, means the left of it. So that is no more relative maximum. Okay, right. So similarly, you can discard the case of f dash of c is less than 0. Okay. So then similarly, you can show that f dash of c is not less than 0. So only possibility is f dash of c is 0. So our result is established now for the case when f has relative maximum at C, that and f dash exists, then f dash of C is 0. Similarly, if C is relative minimum, then you can discuss the similar manner, then f dash of C is 0 whenever f dash of C exists. Okay, and these points C, such points are known as critical points or extremum points. Okay, where the function does not have function is not differentiable. Second thing is function if differentiable, the derivative is value is 0 at the boundary point of the interval if you are considering the absolute maximum and minimum. Okay, right. Okay, so here is the fact. So we have already explained that we cannot drop the fact that C is an interior point of I. So we have already given the example f of x equals to x for x belongs to close 0, 1. And where which derivative is 1, which is non-zero for all x in 0 to 1. Okay, right. So this we cannot drop the fact that C is an interior point of I. Okay. So the second result is immediate. Okay. So f is continuous, and suppose that f has a relative extremum at an interior point C of I. Then either the derivative of f at C does not exist, or if it is exists, then it is equals to 0. So it's include the case that the derivative does not exist. And here is one more modified example you can say of mod x. So f of x equals to mod x minus 2 between x belongs to 1 to 3. You know that function is not differentiable at x equals to 2. 2 is an interior point. Okay, so function is not differentiable, so still f has a relative minimum at x equals to 2. Okay, right. Okay, so now the very important theorem result which you are already aware about it, Rolle's theorem. Okay, so suppose that f is continuous on a closed interval I, and the derivative exists at every point of the upper interval AB. And these points are such that f of a and f of b are 0. They are the zeros of the function. Then there exists at least one point C such that f dash of C is 0. So what is happening is geometrically is, this is the case here. So f of a is 0, f of b is 0. Okay, and function is continuous. Function is continuous and differentiable on the upper interval AB. Then we are able to identify a point C inside AB such that f dash of C is equals to 0, means you have the slope parallel to x-axis. So how will you establish this result? Okay, so how will you establish? So if function is, suppose function is a 0 function.
By definition of differentiation.
Yeah. So function is suppose function is 0 function. Then nothing to prove. Okay, because 0 function is differentiable and 0 function derivative is 0. So we can, without loss of generality, we can assume that f is a non-zero function. That's a very first thing. The second thing is, what we can also assume is function assumes positive values. Okay, assume some positive values inside the interval a to b. If it is not, means suppose f curve is lies completely below the x-axis, that is also possible, means you have this curve like this. Then what you can do is you replace f by minus f. So minus f will go upside. So without loss of generality, you can assume that f assumes f is greater than 0 in for some positive values of I. Okay, now see, f is continuous on a closed interval I. Then boundedness theorem and maximum minimum theorem tells you that function attains its bounds and its supremum and infimum of that set does exist. So what will happen is supremum of f of x such that this range of set x belongs to I exists, and that is equals to f of c for some. Now, since this is possible that f is greater than 0 for some positive for some values of c, so that certainly is greater than 0 because supremum is non-negative, greater than 0. Okay. Now, furthermore, what happen is f of a is 0 and f of b is 0. So certainly, since f of c is greater than 0, so certainly c is neither a nor b. So c must be inside the open interval AB point, AB interval. C must be the interior point of the interval AB. So c is an interior point. Okay, and supremum of f of x is greater than 0, and you know that supremum of f of x is an absolute maximum. You can see, right? Absolute maximum, because it always lies on the right of every value of f of x. So f of x is less than equals to f of c for all for all x inside I. So f has relative maximum at c, and c is an interior point of AB. Then, and since c is an interior point of AB, open interval AB, then f dash exists at c. So in that interior extremum theorem tells you that f dash of c must be 0. Okay, so the very first thing is f is first, if f is identically 0, nothing to prove. If f is not identically 0, then you can surely assume that without loss of generalities, f is greater than 0 for some positive values, for some values. Okay, f greater than 0 on, you can say on some values in I, some points in I. Okay, so this will imply, since boundedness theorem gives you guarantee that f attains its bounds and has its maximum and minimum, that is on I, so you will certainly find a c inside I such that f of c is supremum of this set. Since f of a and f of b are 0, and since f assumes a positive value, so f of c is greater than 0, and f of a and f of b are 0, so c certainly neither a nor b. So c must be an interior point. But we know that at the interior point, the given fact is f dash is exists, the differentiable function is differentiable and derivative exists. So derivative must exist at c. Moreover, since supremum is always a maximum, absolute maximum, okay, means f of x is less than equals to f of c for all x in I. So c is a relative maximum and c is an interior point of AB, then and f dash exists at c, so then f dash of c must be. Okay, so this proves the Rolle's theorem. Okay, so here is the outline of the proof. So without loss of generality, we may assume that f is not 0 and f assumes some positive values. Now maximum minimum theorem implies that the supremum exists at some point c in I. Clearly supremum this is greater than 0 and c is an interior, c belongs to I. Now since f of a is equals to 0 and f of b equals to 0, but f of c is greater than 0, so c must be an interior point of AB. So this so since f dash exists over the interval open interval AB, so f dash of c exists. Also f has relative maximum at c. Hence interior extremum theorem implies f dash of c is 0. So this implies the Rolle's theorem. Okay, and then now I'm going to close this session by establish this result. That's known as fundamental mean value theorem. Okay, so it is not assuming that f of a and f of b are equal and that is equals to 0. Okay, it's only assuming the fact that f is continuous on a closed interval I and that the derivative f dash exists at every point of the open interval AB. Then you will be able to identify a point C such that f dash of C is equals to f of b minus f of a divided by b minus a. So what is the situation here is as follows. So you have this graph. Okay, let me have this graph. So f of A is here and f of B is here. So these are the points A comma f of A and B comma f of B. You can certainly identify the equation of the line of this interval. So this is a f of x. Okay, f of x. You know that what is the line of this? What is the equation of these two lines? This line passing through these 2 points. Okay, so what is that is going to be, I think, x minus a divided by b minus a is equals to y minus f of a divided by f of b minus f of a. The equation of the line of the interval. Now, this phi of x is nothing but this length. So here, this is phi of x is a function. This phi of x is going to be the length of the head. So this is going to be this minus this curve. So that is, if you look at here, this is nothing but f of x minus phi of x is nothing but f of x minus phi of x equals to f of a plus f of b minus f of a divided by b minus a times x minus a. Okay, so this phi of x can be identified by this. So you can look at here. You can relate this with this. Now, what is the property of this function phi? Function f is continuous and differentiable. This is a constant function. This is a constant multiple of x minus a. So this again, so sum of continuous function is continuous and differentiable function is differentiable. So function phi also satisfies properties that which f is satisfying. So phi is continuous on the closed interval AB, phi is differentiable on the open interval AB, and also phi at A, you can verify that phi at A is 0 and phi at B is also 0. So you can apply the Rolle's theorem now. So you will be able to identify a point C in open interval AB such that phi dash of C is 0. And that will imply your mean value theorem result, that f dash of C. So you can differentiate phi. Phi dash of x is equals to f dash of x minus f of b minus f of a divided by b minus. So phi dash of C 0 will give you f dash of C is equals to f of b minus f of a divided by b. Okay, and hence this mean value theorem is established. So in the next session, we will look at the applications of mean value theorem, where this L'Hospital rule is also the one of the application. Okay, and that we are going to look at. Okay, thank you.